using the fact that enthalpy is a state function to figure out values of enthalpy is all described by what's called Hess's Law. So if we remember, enthalpy is a state function, so all we care about is the endpoints. And really where we're going to apply this to is the idea that, say, you want this big reaction. If you want to know the enthalpy change of that, you can figure it out by knowing the enthalpy changes of steps that combine to give the overall reaction. So small changes, if you know the enthalpy for the small changes, whatever big change they add up to, you can figure out the enthalpy for that big change. So Hess's law says delta H for a reaction is the sum of the delta H values of the component reactions. All right, so if we take a look at it, these top two reactions are the small changes, right? Carbon becomes carbon monoxide, then that carbon monoxide reacting to give the overall carbon dioxide. Instead, it could just be the carbon and oxygen reacting all the way to give you carbon dioxide. Well, on the other side, the enthalpies add up to give you, the enthalpies of the small changes add up to give you the overall enthalpy change of the big change. So this is what Hess's law is saying, that if you have small changes, small chemical changes that combine into a bigger chemical change, the enthalpy for that bigger chemical change is the sum of the enthalpies of the small chemical changes. So we're going to look at some different applications and some different facets of this, kind of work through it a little bit at a time to where we can put it all together to figuring out how to use this in kind of a useful way. So we want to look at combining reactions. We're going to show how you can, this idea of the two small changes add up to a big change. Let's take a look at actually working out how that happens when you combine small reactions into a single overall reaction. So combining reactions, we can see I have carbon plus oxygen gives me carbon monoxide. Carbon monoxide plus oxygen gives me carbon dioxide. And so there's a bunch of related compounds, and all carbon and oxygen are the only elements in here, so everything's related. And so when we want to add them together, what we can do is we can imagine that this arrow is similar to like an equal sign for like an algebraic expression. This is everything on the left-hand side, and this is everything on the right-hand side. So all of the reactants for both are going to combine into basically all being reactants for one single reaction. So I'm going to have the carbon solid plus that 1/2 O2 plus CO gas plus, gave myself too much space, 1/2 2 gas filled up. So those are basically, you can see reactant, 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 just put them all together, listed all on one side. And then for my other two, CO gas plus CO2 gas. And so that is where I'm going to be looking. And so that's the first step, is put everything together. And now we want to go through the process similar to, again, algebra, we want to simplify it. And so the thing we want to find, first off, is what shows up on both sides. Because remember, when we first talked about balancing reactions, we said that we didn't want to have anything that appears on both sides of the equation. So if we can see, I'm having carbon plus oxygen plus carbon monoxide plus oxygen gives me carbon monoxide plus carbon dioxide. We want to cancel those out. That's not a net change. So we cancel that out. We would be left with, we now have just the carbon plus 1/2 O2 plus, that's gone. 1/2 O2 becomes just CO2. So the carbon monoxide is not a net change, so we want to get rid of that. And then the other thing we want to do is we want to see, these are the same thing, but they're on the same side of the reaction. So we don't need to cancel them, we instead need to combine them. Those are both 1/2s, add together to give me 1. So solid, or carbon solid plus 1/2 plus 1/2 is 1 O2 gas, gives me CO2 gas. So what we can do is we can combine these reactions. What this is the kind of algebraic process, or the kind of the functional actual process we go through. But what's really happening is if you do this reaction and this reaction, so in this kind of instance, we're thinking about it as 2 steps. If you do step 1 and step 2, that is the same thing as just accomplishing this change. You're turning carbon and oxygen into carbon dioxide. Here, you turn carbon and oxygen into carbon monoxide, and then you turn carbon monoxide into carbon dioxide. That's the same thing as just carbon and oxygen becoming carbon dioxide. There are other modifications we can do to just single reactions. The first one is we can swap the direction of the reaction. So for example, 2H2 plus O2 gives me 2H2O. So I'm saying that these are my reactant chemicals, and here are my product chemicals. The thing is, and there's a delta H for that, negative 572. The thing is, chemicals don't know what they are, right? They can undergo just rearrangement of bonds. So it's certainly possible that we could say, well, what about rearranging the bonds such that it starts as water and becomes hydrogen and oxygen? If we can do it in one direction, it has to be possible to do it in the opposite direction. Not necessarily easy, but possible. And so in this case, if you wanted to go from, if you combine hydrogen and oxygen to make water, it is quite exothermic. You release 572 kilojoules per mole. Well, if you swap the direction of the reaction and say, well, what happens if I go from water to hydrogen and oxygen? The values for the endpoints are the same. The only difference is what you're calling the start and what you're calling the end. So initial and final have just swapped designations. And so the distance between those points is going to be the same. And when you do the subtraction, it's just going to be positive. So if you know that the reaction in one direction is exothermic to a certain extent, in this case 572 kilojoules per mole, the opposite direction has to be endothermic in the exact same extent. If doing the reaction, hydrogen and oxygen gives you water, releases energy, going water to hydrogen and oxygen has to take in energy, and it takes in the exact same amount of energy that the other direction released. So swapping the direction of a reaction just swaps the signs. So you switch sides, you switch signs. The other change we can do to a single reaction is we can modify the coefficients. You're going to note that we're going to start to get a little, we've had some rules about simplifying coefficients and having whole number coefficients that are going to kind of start to go out the window with these thermodynamic rules, where we're going to start seeing fractional coefficients, and we're going to see kind of coefficients be whatever we want them to be. And the thing is, we just need to be consistent. Things still need to be, reactions still need to be balanced, but what we can do is we can multiply all of our coefficients by a constant value. So if we look at this hydrogen and oxygen makes water, it's 2 hydrogens, 1 oxygen, 2 waters. We could take all those numbers, multiply them by 2, such that it'd be 4 hydrogens, 2 oxygens, and 4 waters. That's all still balanced, and the delta H gets multiplied by that same factor, in this case, a 2. When we go, we could do it again, another 2. It's 8 hydrogens, 4 oxygens, and 8 waters. The delta H gets multiplied by 2 again. Going from the top to the bottom line is multiplying by 4. And we can do anything we want. We can also use fractional coefficients. So we could multiply by 1/2 to get what we wanted in there as well. And so you're going to end up, we are going to start to see fractional coefficients, and that's totally okay because we're just kind of working through these things in a way to kind of fit puzzle pieces together. We're not necessarily going to follow as many of our rules. And then again, we're also, when you use moles, you can have half a mole. You can't have half a molecule, but you can have half a mole. All right, based on the following reaction, what is delta H2 for the reaction below? So one of the things I want to point out, it can get pretty confusing when you're just starting to talk. You have a lot of delta H's. Hess's law is all about taking information that you know about a reaction, so you have to know some delta H's, and trying to figure out some other information. So we want delta H2. Basically, we're just saying that this is reaction 2. We already have information, delta H1, this is reaction 1 up here. So I have reaction 1, silver plus 1/2 Cl2 becomes AgCl. and I want to know the delta H for 2AgCl becomes 2Ag plus Cl2. So what would be the delta H for that bottom reaction? Again, that fractional coefficient, if you think 1/2 mole, works just fine because there's a lot of molecules there still. All right, let's work this out, see how it goes. Okay, so based on the following reaction, what is delta H2? So we can see this kind of world where we're dealing with Hess's law, we're going to have basically some sort of reaction with a given delta H. And we're going to want to use this reference equation to determine information about our target equation or equation of interest. Lots of different language for this, but this is always going to be called a reference equation. So I'm going to start using subscripts here to denote which equation we're kind of talking about. Is it 1? Is it 2? So on and so on. And so if we look at this idea, I got silver plus chlorine gives me silver chloride, and I know the delta H for that. And so that's the reference. So for my target, I have silver chloride becoming silver and chlorine. So what's the delta H for this other reaction? And we can certainly see that they're related. The fact that it's all silver and chlorine in both of them, that kind of implies that definitely Hess's law is going to be the way to go. And so what we want to do is look at how are they we know there's a lot of things that are similar. Well, how are those similar looking things different? And so one of the things we can see is that I have AgCl and AgCl. But I can see they're on different sides of the arrow, right? It started out as a product. In my target, it's a reactant. So the first thing I can see I need to do is I need to switch sides. I've just changed the perspective of the reaction. Is silver chloride a product? Am I making silver chloride? Or am I reacting the silver chloride? And so I know switching sides of the chemicals is the same, leads to switch the sign of delta H, which would be the same thing as multiplying by a -1. So we know that's going to be one way that we need to change it. The other thing we can see is that not only is the silver chloride on a different side of the reaction, it also has a different coefficient in front of it. Okay, here it has a 1, here it has a 2. And so that'd be 1 times 2 to give you 2, and you can see this is actually consistent for everything. The 1 in front of the elemental silver becomes 2. The 1/2 in front of the chlorine becomes 1. So what we can see is that all coefficients are times 2. So what that leads to, what that means is we want to do delta H1 times 2. So we can see there are 2 differences between my reference equation, which I have a delta H for, and my target equation, which I want to know the delta H for. And basically I can parse out what are those differences. Each of them has an associated change in how we would look at, how the delta H is related. And so we can put those together. We can see that delta H2, my target, is going to be -1 times 2 times delta H1, where this comes from swapping my signs. I need that -1, and this 2 comes from my coefficient change. And so what I can do is I can just plug in this right here. That is -1 times 2 is -2 times -127 kilojoules per mole. And if I do that, I would get that delta H2 is going to be equal to 254 kilojoules per mole. And so we can see that using this reference equation, which came from someone doing, say, an experiment, someone actually ran this equation and saw what's the delta H for it. And we can use that to figure out the delta H for a different related equation that we can avoid having to do that experiment on. So Hess's law is going to be really useful. We can see some, we started with, this was an exothermic equation, right? If you want to make silver chloride, you release energy. Our other equation was endothermic, because if you're going to break apart silver chloride, you need to put that energy back in. So in order to undo it, we would think we'd switch from being exothermic to endothermic. And because the coefficients are all larger, we're just dealing with a larger scale of energy, which is why that goes up to 2.